Hello and welcome back. We will cover section 5.3 in this video, which is all about the Poisson distribution. And let me tell you the definition, and then this will be a lot like the distribution we saw in the previous section, the binomial distribution. So the Poisson distribution is again a discrete probability distribution that counts events over an interval. And that interval can be some time period, it could be some length or area or volume or anything that's describing some sort of space or time, essentially. So, for example, a Poisson distribution could describe the number of phone calls you receive in a day. Again, the day is going to be the interval over which we're measuring, and each phone call is going to be the event that we're counting. It could be the number of hurricanes that occur in a year, or the number of frogs in a square mile. So again, it could be the how many objects we find in some area, how many sort of events take place over the course of some time period, and this will seem a lot similar to the binomial distribution that we saw before. So here, we can look at two similar examples. One is the number of free throws made in 10 attempts, and here's the number of free throws made in a minute. So there is a difference here. In one, there are 10 trials, and we're looking to see how many successes there have been made in those exact 10 trials. In another one, we have an interval. We have some sort of length of time, and we're counting how many free throws that we make. Here, this is a binomial distribution, and this is going to be a Poisson distribution. So the binomial distribution is counting successes in a number of attempts or number of trials, and the Poisson distribution is counting events over an interval. So they are different. They can be used to approximate one another. If you make a lot of attempts, as in there's a large number of trials and the probability of success is really low, binomial distributions are very similar to Poisson distributions. However, they are different, so it's important to recognize the difference. Are we looking at a number of trials, or are we looking at an interval? The formula for the Poisson distribution has quite a few parts. So the probability that an event occurs X times within some interval is mu to the X power times e to the negative mu all over X factorial. Okay, let's break this down. So X is the number of times the event occurs. Mu, like usual, is going to be the mean. So this is going to be the mean value of X. And E here is just a number. So E is approximately 2.78, I think 1828, so on and so forth. This is an infinite decimal. It doesn't repeat, so this is an irrational number. This is just a fixed value. It doesn't change. It's not a variable. It's a static constant. So E is a number that we know ahead of time. X is what we're calculating the probability of, and we have to have some information about how often this event occurs. So we need to know mu, which is the mean, in order to calculate, well, is X likely, or is X too big, or is X too small? Well, we can compare it to the mean. So let's go through an example where we plug this in. We've got a plot of land, and it's divided into 118 meter by meter squares. So we just section it off, and we go through and we count how many frogs we can find. And we count 73 frogs. So the question is, what's the probability probability a square has exactly 2 frogs? Or what's the probability that one of these squares has 0 frogs? Or probability that one of these squares has 10 frogs? So we need to, let's focus on one of these. Let's focus on 2 frogs for now. So we need to know all of our numbers here. So x is just going to be the number of times that the event will occur. So x here is just going to be 2 frogs. But we also need to know the mean. And we know that we found 73 frogs in 118 squares. So if there's 73 frogs in 118 squares, that's going to be, I did this calculation beforehand, 0.6186 frogs per square. So on average, we're going to have 0.6 frogs in each square. Now you can't have 0.6 of a frog. That would be kind of gross. But what this means is that on average, the mean will be 0.6. Some squares will have frogs, and some squares will have no frogs. So now we can plug everything into our formula. The probability that a square has exactly 2 frogs is going to be, we take the mean, which is going to be this number, so 0.1868. We raise it to the x power. We're going to take this times e raised to the negative mean, which is going to be 0.6186. And we divide by x factorial. Remember that factorial just means we multiply all the numbers from that number down to 1. So 2 factorial is just 2 times 1. Now, this is not something that I would ever expect you to do by hand, so we would just plug this into a calculator, and what we end up with is 0.5387. So here, this says that the probability, excuse me, I wrote down the wrong number. And the probability for 2 is 0.1031. My apologies. So here, the probability of finding exactly 2 frogs in any square is going to be about 10%. So you'd expect that 10% of the time, if you checked a square, there'd be 2 frogs. Let's find the probability that there are 0 frogs. So again, the mean doesn't change. The average number of frogs in a square is always just going to be about 0.6. However, the number that we are checking is going to change. So again, e doesn't change, the mean doesn't change, only x changes. And 0 factorial is a special case for the factorial. Just so you remember, 0 factorial is equal to 1. So again, we can plug this into a calculator, and we get that the probability that we have 0 frogs in any one square is about 53%, a little over 53%. So over half the time you'd expect there to be 0 frogs in a square, which makes sense because we only found 73 frogs in 118 squares. Most of quite a few of the squares aren't going to have any frogs in them at all. So if we continue and we look at a pretty big number, 10, what's the likelihood that we find 10 frogs in one square? Well, on average, there's only a half a frog in a square, so 10 seems pretty unlikely. So let's check. Again, we plug in all of our values. The mean hasn't changed. E never changes, it's just a constant. But now we're looking at 10 frogs in an area. And it turns out that if I write this in scientific notation, this is going to be 1.21 times 10 to the negative 9th. Now, times 10 to the negative 9th, this means that I'm going to put 8 zeros here. So this is pretty darn close to 0, but it's a little bit bigger. So the notation that the book uses is 0 plus, meaning it's not impossible that we could find 10 frogs in a square, but it's very, very unlikely. The probability is only slightly bigger than 0. So again, it's just this formula, and we apply this formula a bunch. Here's a question. I looked up some data from 1952 to 2017. There were 413 tornadoes in Montana. I should clarify. So the question is, what's the probability that there was more than one tornado in a year? Now this is a little bit tricky, because we would want to find the probability that there was 2 tornadoes, plus the probability that there were 3 tornadoes, plus the probability that there were 4 tornadoes, plus and so on and so forth. Well, that's a lot of numbers, and in fact, this won't end, because I could have the probability that there were 100 tornadoes, probability that there's 1,000,000 tornadoes, probability that there's 1 billion tornadoes. This would go on forever. So I need to find a better way to do this, and what I'll do is I'll use the complement. So instead of finding the probability that there's more than one tornado in a year, I'm going to look for the complement, which is going to be the probability that there was 1 or fewer tornadoes. And with the complement, I'll just take 1 minus that value, and we get the probability. So I'll need to find the probability that there is exactly one tornado, which means, I'll need to find the probability that there's 1 tornado and the probability that there were 0 tornadoes. This is a 65-year span, so let me do a little bit of scratch work. From 2017 to 1952, that's 65 years. And if there were 413 tornadoes in that time, over 65 years, that means that there was an average of, I wrote this down, 6.35 tornadoes. So this was the average. So this is the mean. So when I'm looking for the probability that there's exactly 1 tornado, what I'm going to do is I'm going to take the mean, raise it to the x power. So x here is just going to be 1, since we're looking at 1 tornado in a year, times e raised to the negative mean power, divided by the number of tornadoes that we're looking at, factorial. Doing this, I got 0.0111. So about 1% of the time, we would expect to have exactly 1 tornado. For 0, again, the mean doesn't change. The mean is just the average number of tornadoes. Nothing changes there. E is again just E. It's a number. But now we're looking at getting 0 tornadoes in a year, and this probability is even smaller. This probability is 0.017. So the probability that there were 1 or fewer tornadoes in a given year, I'm running out of space a little bit, the probability that there were 1 or fewer tornadoes, this is going to be 0.0111 plus 0.0017, which is 0.0128. So it's just a little over 1%, which means that the probability that there's more than 1 tornado is going to be 1 minus this, 1 minus 0.0128, which is in fact 0.9872. And I'll very quickly end with some parameters. When we look at a Poisson distribution, the mean and the variance are actually equal to one another. which means that the standard deviation is the square root of the mean.